Вот.
Так.
Так, вот я зашел, надел на
Так.
работать.
Вообще. То есть можно начинать, да?
Кажется, вот вы сейчас что-нибудь скажете, чтобы...
Хорошо.
Нет, компания.
А. Okay, so let's start. I'm glad there are much fewer people now than next time. Hopefully next time, essentially nobody will show up. But still, if somebody survives, you are very welcome to submit your home assignments. Say in hard copy, or send them to me via email. Okay, so last time we gave an abstract definition of an affine algebraic variety, and we claimed that there was an anti-equivalence of categories. Between affine algebraic varieties and morphisms. Finitely generated commutative unital K algebras without nilpotence. Well, in fact, there are two equivalences. Given a variety X with the sheaf of regular functions, we associate to it just the global sections, so to say, OX of X, or else K of X. These are just equivalent notations. Global regular functions. Okay, and in the opposite direction, given an algebra A like this, we associate to it some variety which is called spectrum of A. But then I didn't give this definition last time, and we will start with it now. So what is the spectrum of A? Or else, maybe more rigorously, it should be called the maximal spectrum. Spectrum maximum of A. Okay, so as a set, this is the set of all homomorphisms, algebra homomorphisms. From A to our base field K. And the kernel of such a homomorphism is certainly a maximal ideal in A. So, in other words, this is the set of all maximal ideals such that the corresponding quotient algebras just coincide with the base field. But then we'll prove a little bit later on, and it's essentially Hilbert's Nullstellensatz, that this second second addendum is not necessary. So we will see that for any maximal ideal M in A, automatically the quotient is isomorphic to the base field. Okay, so this is the set of all maximal ideals. Okay, so for this reason, it's called the maximal spectrum. Okay, and let me just say a few words that you don't need to understand or remember, that there is another notion due to Grothendieck, just of the real spectrum, not maximal. This is the set of all simple ideals, or prime ideals. I in A.
Они как ноль совпадают, эти два.
Yes, so far I said nothing about topology, yes? So I will in a moment, but so far I just defined the set. Huh? If that wasn't the question.
То есть я правильно понимаю то, что в качестве спек мы берем не все простые идеалы, а именно максимальные?
Yeah. We will take only maximal ideals, but there is another notion that is commonly called spectrum nowadays. It's the set of all prime ideals, not necessarily maximal.
Почему гомоморфизмам не могут отвечать одинаковые максимальные идеалы?
Well, I would say it's sort of tautology, but not topology, but tautology. Yeah, because maybe for this reason, one goes to one, and it's K algebra. Yeah. Okay, but maybe in the second semester we will do just this. But so far, if we used this definition, then we won't be able to associate to elements of the original ring A functions on the spectrum, because these functions on the general prime ideals would not take values in this base field K. For example, in the zero ideal, they will take values in the fraction field of A, in some bigger field. Okay, so let's forget about it for the time being. And now the topology. It's called Zariski topology. And it's somehow lifted from functional analysis along with terminology. Like maybe Israel Gelfand and Mark, not Neimark. I mean, if you have a linear operator, maybe an endomorphism, say x from V to V, then from linear algebra you probably know the notion of the spectrum of a linear operator. Yeah, but on the other hand, you can consider the algebra generated by this. By x. If it's infinite dimensional, then there are some topological or functional analytic I don't know, say difficulties, but then maybe you can take some topological closure of this polynomial algebra or something like this. But anyway, the spectrum of this algebra in that sense coincides with the spectrum of this operator in the usual linear algebraic sense. So, spec A is just the same as spec X. Maybe I shouldn't call it X because X was our variety. Something else. Like what? F. Right. Sorry. Okay. So the Zariski topology. In fact, last time I had an example of Zariski topology in one-dimensional case, yeah, for a fine line or projective line, and then the closed subsets were finite subsets, and probably everybody heard how to generalize it to the arbitrary dimension. Yeah, the closed subsets Z inside the spectrum of A, by definition, are the zero sets of arbitrary subsets F in A. So what does it mean? You see, given an element A in our algebra, we can end an element X in its spectrum. So X is a homomorphism from A to K. It makes sense to evaluate A at X. Yeah? Say A of X, just by the very definition, well, it's the same as evaluation at X of A, and by the very definition, this is just X of A. Okay? So you somehow view your original algebra as the functions on its own spectrum. Okay, so this way, this evaluation is a map from A to just all functions on the spectrum. Okay, and in this sense, I may say that an element of A viewed as such a function vanishes somewhere. Okay, and now I take an arbitrary subset of A, and I take its common zeros. Okay, so this is called Z sub F in the spectrum of A. So these are, by definition, all the closed subsets. And if we are back to our example of the affine line, then our algebra is just polynomials in one variable, and any polynomial has finitely many zeros. So if you have a few polynomials, their common zeros are inside of zeros of each one of them. So you get the finite subsets. Okay. So for the fine line, you get the same topology as we discussed last time. Okay. Now note that if you generate the ideal by this subset, and then the zeros of f are the same as zeros of this ideal. So it's enough to consider, as these subsets, it's enough to consider ideals. We'll gain or lose nothing. Okay, so once again, the closed subsets of the spectrum of A are just of this sort, zeros of some ideal. Now we have to check that they satisfy the basic axioms of topology. So, for example, the empty set is the zero set of what?
Of one.
Yeah, for example, of just one. Or in other words, of the whole ideal, yeah, which coincides with the ring A itself. And now the whole thing, the whole spectrum of A is the zero set of what? Of zero. Yeah. And now the ideal coincides with this set. Now if we are given two things, say Z I1 and one take in union with Z I2, then how would we write it in the similar way? It's the zero set of what? Yeah, but in the community of algebra it's the same, yeah, so it's Z I1 intersector I2 or I1 times I2. Okay, and if I wanna take the union, but now the union, sorry, intersection, but now the intersection may be already infinite. So intersect over some set of indices, I alpha. Then what is this? Yeah, like this. Okay, so the basic axioms work, and this is our topology. Now we have to specify the sheaf of regular functions. Yeah, this is the most important thing. But by the way, let me stress once again that this is really the most important thing, that the sheaf of regular functions is by no means determined by the topology of X. Yeah, for example, any curve like A1 or P1 or whatever, this or that, or elliptic curve, any curve at all, say over complex numbers. As a set, it is just an uncountable set like C. So it's bijective with C. And topology is just a finite subset topology. closed subsets are finite subsets. So from this point of view, all of these guys are the same. So what really distinguishes them is the sheaf of regular functions. So you really have to, this is a new piece of data, essential piece of data. Okay? As opposed to what you might be used to in usual analysis or whatever, you really do need to specify the regular functions. Okay. So we have to specify the regular functions. So I have an open subset U, and what are the regular functions? So OX of U. These are functions f such that there is an open cover like this, such that f restricted to ui is a rational function. Well, okay, so I didn't erase, luckily, this evaluation homomorphism. So it's evaluation of AI over evaluation of BI. Yes, that's important. And AI and BI are some elements of our algebra, but BI does not vanish on UI. I mean, never vanishes. Not as identically zero, but never vanishes at all on UI. Okay. And now, by the very definition, this is some local definition. So by this very definition, such things do form a sheaf. Get a sheaf. And only we have to check that given such f, its non-zero level set is open, df which x? Oh, x is just the spectrum of A. And f inverse is a regular function on this open set. And this is clear, I think, Gabby, because again, this openness is a local property, and on each open set it's clear, and then you can invert this function on each open set. It will be of the same sort. Yes, so I think it's clear. Pardon me? Pardon me?
There are two different F inverse.
Oh, sorry. Yeah. Sorry. Sorry. Thank you. Sorry about this. Yeah. Okay. So we do get some variety in the definition of the absolute definition of the previous time, and we have a homomorphism, evaluation homomorphism from A to the global regular functions of this variety. This is the spectrum of A. And the first thing to check in our ambitious program is that this is an isomorphism. Okay, so to check, among other things, that evaluation is an isomorphism. Okay, and the very first thing to check is that it is injective. Okay, and in other words, it means that there are sufficiently many maximal ideals. Yeah, because we evaluate at the points that are maximal ideals and have enough of them. And this is one of many equivalent forms of Hilbert-Nullstellensatz. For example, this claim is equivalent to Hilbert-Nullstellensatz. So you may just use it as a formulation of Hilbert-Nullstellensatz, but since maybe somebody does not remember this Hilbert-Nullstellensatz on the spot, maybe let me formulate it in the classical form and even prove it. So I will make a digression. Nullstellensatz. Well, in fact, I will give at least two different proofs, and one of them will be an honest, good proof, but it will be rather long, so I will give it later on. And now, just to help you psychologically, I'll recall the statement and give a dirty trick, but very short proof. Well, as you might guess, this is due to some Jews. One of them is Amitsur, around 1957. Another one is Rabinovich in 1929. Maybe let me first formulate it this way, that any maximal ideal M in the algebra of polynomials, say over complex numbers, okay, let it be complex numbers for a moment. Is of the form MA, where A is the point A1 and so on, AN. So it is generated by linear forms x1 minus A1 and so on, xn minus AN.
Прямая А и вот такая закругленная это одно и то же?
Calligraphic A is an arbitrary algebra without nilpotence. And this is a particular polynomial algebra. So arbitrary A is a quotient of this strict A. Straight A. Okay, so in fact, any maximal ideal with the quotient C is of this form. Any M such that A over M is isomorphic to complex numbers is necessarily MA for some A. Okay? Just because if evaluate and any coordinate must vanish somewhere, and this AI is where it does vanish. Okay, so what we have to prove is that there is no surjection from A to a field which is not complex numbers. So assume contrary, that there is a maximal ideal M such that the quotient A modulo M is not C, it's not complex numbers, and then we will arrive at a contradiction. So if it's not complex numbers, then it's bigger. But if it's bigger, it must be of transcendental degree at least 1. So let's call it K, and it's not complex numbers. So then K contains just a rational functions field like this. Yes? So we have a surjection from A onto this K. And what is bad about this? The bad thing is that the dimension over complex numbers of A itself is countable. Right? Because it has a basis, namely 1, x1, and so on, xn, x1 squared, x1, x2, and so on. So it's a countable basis. Okay? But unfortunately, the dimension of this rational functions field is uncountable. Or maybe rather, fortunately. Why is it uncountable? Does anybody know?
Because functions of only one
Right. Absolutely. Yes, great. Thank you. And how do you know this? Did you know this dirty trick of Amitsur?
I think I heard it some time ago, I forgot, and now.
Great.
How do you get the ring of rational functions is inside K?
Because complex numbers are algebraically closed. And if this field is bigger than complex numbers, then it must contain at least one extra element. Let's call it T. But this T does not lie in complex numbers, so it must be transcendental over it. Right? Because C is algebraically closed. So the dimension is uncountable. Since 1 over T minus C whatever alpha are all linearly independent for different C alpha. And why is this? So suppose there is some linear dependence, so the sum of A alpha times 1 over T minus C alpha is 0. Then what?
Домножим на произведение всех и поставим число.
Yeah. Okay, great.
То есть это не работает, если более...
Yeah, but if our field is QQ bar, for example, countable, yeah, then it doesn't work. Yeah. So it only works for C, but not necessarily for C. For any algebraically closed uncountable field. So this proof works for any algebraically closed but uncountable field. Okay, but now there is another dirty trick.
Can you
Yes.
about case when quotient was just a C? Why our ideal?
Pardon me?
Case when A factored by M is isomorphic to C, then what?
Then nothing bad. It's one-dimensional.
So well, what is A?
What is this A?
Yes.
It depends. There are many maximal ideals, but all the maximal ideals are this sort.
No. If we have case that our arbitrary maximal ideal is that factor by maximal ideal is isomorphic to C, while this maximal ideal is MA.
Just because we have to take the evaluation, and then let's take a x1 modulo this m. It lies in complex numbers, so it's some element of complex numbers that I will denote by a1, and the same for all the other coordinates. Okay. Fine. So the dirty tricks continue. There is Solomon Lefschetz. Principle that any two algebraically closed fields of the same characteristic are elementarily equivalent. It's something from logic. So if you can write down and prove some formula, some finite formula in one of them, then it is true in any other. Okay. So what distinguishes algebraically closed fields is only their characteristic. Yeah, for example, there's a formula like this: x plus x equals 0 for any x. And then it means that characteristic of your field is true.
But of course there is non-isomorphic fields of same characteristic.
Certainly they are non-isomorphic because they are of different cardinality, like countable and uncountable fields. Certainly they are non-isomorphic, but they are elementarily equivalent.
What does it mean?
It means once again that when you write any algebraic statement like this, then it's simultaneously true or false in all such fields.
It can be only equality or like non-equality.
No. Well, inequality, I mean, not like this because there is no notion of order, but certainly you can use such because it's just negation of equality. Just any logic operation, any predicate or whatever. Yeah. Okay, so there we are. We proved it for uncountable fields, but the statement itself is of algebraic nature, so it works for any fields at all. Okay.
Сказать то, что, значит, если мы предположили, что К равняется К содержится С, то тогда этот иногда К будет размерность его будет на С.
Yeah, it's possible because this is small, countably dimensional, and this is big, uncountably dimensional. This is impossible. Such a surjection is impossible.
Okay.
Вообще есть еще алгебраический замок?
Oh yeah, for example, F P bar and Q bar are all the smallest, so to say, and all countable algebraically closed fields. Okay, so maybe a corollary. That if we have an ideal J in our polynomial algebra, and we know that the corresponding set of zeros is empty, then this ideal is the trivial ideal. And this is already maybe closer to some of the standard formulations of Hilbert, Burchtel, and Zatz. So the proof is very simple. So if J is strictly smaller than A, then it is contained in some maximal ideal. Okay, and then we already know that this maximal ideal is of the sort MA, but all the elements of this MA vanish at point A, in particular those. The J contains A. Okay, but in this argument, we have used this maximal ideal, and to prove the existence of maximal ideal, you need a Zorn lemma, unfortunately. Yeah. And it's equivalent to axiom of choice. And it's part of dirtiness. So later on, I will give another proof that does not use Zorn lemma or axiom of choice. Yes. But algebraically closed.
Можно еще, что вы сказали по модулю этой ленты Зорн?
I said that, if my ideal is not the whole ring, then it must be contained, well, it's a proper ideal, and among the proper ideals, there are maximal ideals. So there must be some maximal ideal containing this J. But any maximal ideal does have common zeros, as we just argued in the previous part. Yeah? Well, so all the elements of this ideal do have common zeros, because they lie in this maximal ideal, whose elements all have common zeros. Okay, and now there comes the Nullstellen Satz in the most classical formulation. Where did we use algebraic closeness? Because we constructed this homomorphism from A to an extension of our base field, and if it were not algebraically closed, this could be a finite extension. For example, real numbers, complex numbers, and then this argument wouldn't work through. Okay, so Nullstellen Satz itself. Suppose we have some ideal J, and it has some zero set Z sub J inside just An. Okay, so we're talking only about this polynomial algebra so far. Then we'll return to general algebras in a short while. Now, given an element f, a polynomial. Suppose that it vanishes on the zero set of this ideal. For example, it could be an element of this ideal, but not necessarily. It could happen that f to some power could lie in this ideal. Yeah, and Hilbert-Null-Stellensatz says that nothing worse could happen. Okay, so in other words, f lies in the radical ideal of J. So this is the set of all functions phi such that there is some capital N such that phi to the capital N lies in J. By the way, maybe let's check that this is an ideal. Yeah. But still, for example, why does the sum of two elements lie there? Phi plus psi. Yeah. To the power n plus m, something like this. Okay. And for the product by anything, it's clear. Okay. So this is the common, the most standard formulation of Hilbert-Null-Stellensatz. That, in a sense, there is sort of bijection between Zariski closed subsets and ideals. Namely, to each ideal we associated its zero set that was by definition a closed subset in the affine space. But there is some sort of inverse procedure. Yeah, given this zero set, we can consider the ideal of elements which vanish on this zero set. And then it can be bigger than the initial ideal, but not much bigger. And in fact, it means that it's a good thing that we have this. Because if we consider the quotient algebra, A modulo J might have nilpotence. Yeah, for example, like polynomials in one variable, modulo it's cube. Okay, but when you take this radical, then by the very definition, this quotient does not have nilpotence. And in our full semester, we only work with such algebras, with algebras without nilpotence. So we automatically get them from Hilbert-Null-Stellensatz. Okay. Okay. So now let's prove this. And this is the proof of Rabinovich that I advertised. But again, one dirty thing about it, that it uses Hilbert basis theorem. Oh no, it doesn't matter at all, absolutely. We never used zero characteristic so far. How do you mean? How do you mean? Certainly we did. We would take any algebraically closed uncountable field of characteristic 2, for example, Yeah.
Для чего тогда мы вообще использовали вот этот принцип?
We say take f2 and take many variables like this, t alpha, and here alpha lies in complex numbers. Many independent variables. Okay, and then we take its algebraic closure, and it's an uncountable field of characteristic 2. And for it, the same Amitsur argument goes through, but then all the algebraically closed fields of characteristic 2 are elementarily equivalent. So we get the same statement for f2 bar. But all this is very dirty. I warned you in advance. Yeah. In particular, here we'll use Hilbert-Basis theorem. I will prove it afterwards, next time maybe. And also I will give another proof of Hilbert-Nurstein-Zatz without use of Basis theorem. But so far, let's use it. So this ideal has finitely many generators. Like this. Okay, now let's consider an auxiliary ring, polynomial ring, but we attach one extra variable z. Okay, and here we consider the same elements, f1 and so on, fr, and also 1 minus zf. Okay, f is our function of interest. We are going to prove something about f. Now we know that these guys do not have common zeros. In A n plus 1. Right, just because we know that f vanishes on the common zeros of those guys. Okay, but then minus this, that does not vanish. Okay, so then by the previous corollary, it means that we can express just the unit element via those. We can write down 1 equals, say, g1 f1 plus g2 f2 plus so on, plus some g times 1 minus zf. Okay, and now let's substitute. Z equals 1 over f, just formally. So these f's are polynomials in x1 and so on xn. They're independent of z. But these g's, they're already functions of z, of some maybe high degree. Okay, so this whole expression depends on z, and we will get high degree denominators after such substitution. But let's multiply by some power. By f to the power n to kill the denominators. Okay, so what we get is f to the power n, we'll multiply the left hand side, is h1 f1 plus so on plus hr fr. And that's exactly what we wanted to prove.
But
yes.
This h can depend on this j1 can depend on that. Yes.
Certainly, but then yes, they do depend. But now we substitute 1 over f to this z, and now z does not exist anymore. Now everything is in terms of original axis.
То есть, получается, мы убиваем 1 минус zf?
Yeah. Well.
А что мы умножаем на
Как мы использовали какой-то?
Типа у нас было равенство многочленов для любого z, мы взяли данного понятия
Yeah.
конкретного элемента.
Yeah, we just specialized at this substitution. In particular, this cancels out, and we only have that.
Just applies f.
Pardon me?
Да, я правильно понимаю, что это типа как, на самом деле, это как домашнее задание, где мы добавили формальный обратный 1 делить на f, вот это доказательство. Ну, как бы z это же 1 делить на f у нас получается, да?
Yes.
Свойство такое, что он обратно все.
Yes, well, if you want, if you wish.
Почему 1 делить на f существует? Потому что мы в zg.
No, it's just a formal substitution. Just formally, absolutely. Like, well, so suppose I only use that there are no zero divisors in the ring of polynomials. Yeah.
1 делить на f это рациональная функция.
Yeah. So this g1 could be z to the power z to the power 5 times x1 plus x2 cube. Yeah. And so on. And then just substitute formally. Okay.
Как это работает? То есть, когда мы добавили 1 делить на f, мы формально подставили, мы в каком-то кольце работаем.
Yeah, we work in the ring of, in the localized ring, for example, yeah, A, F, for example, here. But there are no zero divisors, so we lose nothing.
Если это какое-то соотношение в локализации выполнено, то оно выполнено и в
Yeah. Mm-hmm.
По тому принципу, о котором вы говорили, да? Или почему?
Because there is such an embedding. Okay. Fine. Now finally we can prove this claim we wanted, that evaluation homomorphism from A, there is a quotient of A, of calligraphic A. To the functions on its spectrum is an embedding. Okay, so now we can prove what we wanted. Our algebra is the quotient of polynomial algebra over some ideal I.
Not a calligraphic A.
Pardon me?
On the top of the blackboard, it's not a calligraphic A, isn't it?
Calligraphic. Sorry, yeah. Sorry. Thank you. And this is. Yeah. Sorry. Yeah, I confused. To A's. So let us take an element in our algebra, and it's the image of some function. Okay, and if this A lies in the kernel of evaluation, then it means that A lies in any maximal ideal of our algebra, such that the algebra over M is isomorphic to the base field. Okay? And we want to prove that under such assumption, A is 0. Okay, but A is a restriction of some polynomial function. So we know that this function restricted to the set of zeros of my ideal is 0, right? Because all the points in the set of zeros, they have such a type. Yeah, they are maximal ideals of A, such that the quotient is K. Okay, but then it means that F lies in the radical of this ideal. Well, in fact, this is true by Hilbert-Nullstellensatz, but I additionally require this. Okay, but this means that the function restricted to our spectrum is 0, but then there are no nilpotents. So A to the power n is 0, but no nilpotents condition means that A itself is 0. And we are done. Okay. Now, yes? Yes?
Мы видели, что f лежит в радикале.
Yes.
А что мы хотели доказать?
We wanted to prove that A vanishes. Here? That's exactly what we wanted to prove. That if a function vanishes on the zero set of some ideal, then it lies in the radical of this ideal. That's the most standard.
Мы вроде бы вот хотели, что А фактор пара радикала не имеет никакого.
No, this is by very definition. This is clear by definition of radical. It was just a comment on the naturality of this notion. The proof of this statement, here is Nullstellensatz, that if we have a function that vanishes on the zero set of some ideal, then some power of this function lies in this ideal. This is the most standard formulation of Hilbert-Nullstellensatz. It's usually formulated this way, though it has many equivalent formulations. Just because it's a function in here, right?
Да. Хорошо, потому что мы поконкретизовали, лежит в А, значит.
Окей.
Скажите, а как обратно доказать, что вот из этого следует то, что направо. Мы же должны эквивалентность двух формулировок. В одну сторону как бы доказали,
well, just apply to the polynomial ring, and then you will, from this you will see that any maximal ideal has this standard form, and then repeat this argument. But that doesn't matter. Don't worry about this. We just from the standard Nullstellensatz we derive this claim. Okay, so we know that the evaluation homomorphism from algebra A to a function on its spectrum is injective. Nice. And now let's maybe also prove the Nullstellensatz for this algebra instead of polynomials. Again, that suppose an element A in this algebra, and given this element, its evaluation vanishes on the standard closed subset given by some ideal J. then A to some power lies in this ideal. In other words, A lies in the radical of ideal J. Okay, just what we had before, only not for polynomial ring, but for arbitrary finally generated ring without nilpotence. Okay, and the proof immediately reduces to the polynomial ring. Let's take an element some B in A without this radical of J, and then B, the image of B in A prime, that is A modulo J, is not zero. Yeah, and hence, sorry, maybe not modulo J, but modulo the radical of J. So then this algebra does not have nilpotence either. Has no nilpotence. And we just by this claim we have just proved, applied to this algebra A prime, there is some maximal ideal that contains this element. Pardon me? Because we quotient out by the radical. Yeah, but by the very definition, just what we already claimed before. Okay, so by the claim, there is some point, some x prime, homomorphism from A prime to our base field, such that B bar of x prime is not zero. Okay, because B was not in this radical. Okay, and we have the composition from A to A prime to our field. So this is x prime, this is the projection, and this composition is x. Okay, and then x lies in the zero set of this ideal on the one hand. On the other hand, B of x is not zero. Okay, so we proved that the set of functions vanishing in A, vanishing on Z J, they lie inside the radical of J. Okay, and also clearly the radical of J has this property. Okay, so we're done with this, and let me derive a couple more useful corollaries. Maybe I should somehow at least numerate them. So maybe for today it's corollary number 2. But anyway, next time I'll forget about this numeration. If f in A is a subset such that the corresponding 0 set is empty, then you can express 1 as a finite sum AI Fi okay, of these elements. So you can express 1 via these elements. And the proof is clear because since this 0 set is empty, then the ideal generated by those elements is well, how to say it? 1 lies in the radical of this ideal. Okay? Because 1 vanishes on the empty set, and by Hilbert-Nullstellensatz, it lies in the radical of this ideal. Okay? So 1 power to the power n is 1 and lies in this ideal. Yes?
This 0 set lies where?
It lies in the spectrum of A.
So it's all homomorphisms that are 0. There is no common.
Yeah, yes. Mm-hmm. Yeah, so this may be an infinite subset, and still there is some finite combination that gives you the unit element. Okay? Just because this is somehow definition of our algebraic operations. When you define the ideal, it contains only finite sums, but by the very definition. Okay, and now the basic open sets. I will introduce this notion df for f an element of A. So df in the spectrum of A is the set of X such that evaluation of F at X is not 0. Okay, so in other words, this is the complement spectrum of A without the 0 set of F. Okay, and by the very definition, these basic open sets form a basis of Zariski topology. So any open set contains an open subset of this form. Okay, but maybe this will be an exercise for your home assignment. But let me just state it. They form a basis of the Zariski topology. On the spectrum, and the next corollary is that now until number 3 is that the spectrum of A is covered by these basic open subsets if and only if how to say it, for any collection n I of positive integers, you can express 1 as a sum, as a combination of powers of those elements. Okay. Well, essentially, I could take ni equals 1, and this will be just a combination as before. But in the next application, I will need the squares. Okay, so that's why I have such a weird formulation. But
we again have f that z of f is empty.
Yeah, because exactly. So the proof is that, as you explained, that the spectrum of A is the union of dFi is equivalent to the claim that the f is empty. And somehow this set of zeros does not change if I replace f by its power. Okay, so I'm free to choose any powers here. Okay. Also, from this argument, again, there's a finite sum. And from this finite sum argument, it follows that the spectrum of A with its Zariski topology is quasi-compact. So any open cover contains a finite subcover. And this again will be a problem in your home assignment, so I will not even write it down. Okay. So we still have some 5 minutes left, and I hope to finish. We had to prove that the evaluation homomorphism from A to the functions on its spectrum, global functions on its spectrum, was an isomorphism. So we already proved injectivity by Hilbert and Stilensatz. And now let's prove surjectivity. Okay. So let's take a function f here. Then by the very definition, there is a cover u alpha, some finite cover, and on each u alpha, f is some rational function like g alpha of u modulo h alpha of u, and I don't write evaluation anymore. On the one hand, to unburden my notations. On the other hand, well, there's no injectivity. So by this injectivity, we identify A with its image under evaluation. Okay, and since those basic sets do form a basis of Zariski topology, we can assume that all those U alphas are basic. Say for some function R alpha, and then since the denominators H alpha do not vanish on those open sets, Then if I multiply R alpha with H alpha, I lose nothing. So d R alpha is the same as d R alpha times H alpha. Okay, so for this reason I can just multiply everything here by R alpha and assume that H is just R. So I can rewrite it as R alpha of u times G alpha of u over R alpha of u times H alpha of u, and so can assume that R alpha is just the same as H alpha. Okay, fine. And now
Alpha is equal to H alpha alpha.
So once again, when I write this, my open set that does not change, so I can take for R alpha this product, and this will be just the denominator.
This means that R alpha is equal to H alpha R alpha.
I can replace here.
Okay.
Yeah. The denominators. So my functions are locally rational functions, right? Yeah, with some denominators. These denominators do not vanish on those open subsets, and I can assume that those open subsets are exactly the basic open subsets for those denominators. I lose nothing by this assumption. Okay, and now let's consider H alpha squared times f over on u alpha, or maybe just this function. Well, let's consider H alpha squared times f. Then on the open subset D H alpha, it equals what? H alpha times G alpha, yeah, and vanishes on the complement. So spec A without D H alpha. Okay, so it is really a function in A. Okay, so H alpha squared times f lies in A. It is this function. Okay, this regular function, a global regular function in A.
Почему не может так оказаться, что
Yes.
если мы умножим R альфа на F, H альфа мы получим 0, например? Можно?
No, because none of them vanishes at this open set. They are both invertible on this open set, so they cannot have a zero product. Okay. Now, by this previous corollary, since the spectrum of A is covered by those basic open subsets, you can express one as such a combination. So you can write down corollary. Yes, it's just an element of A, right? Because it is defined everywhere. It's on the complement. It's 0. It is. It is this function. Okay, this function, so it lies in A. So by corollary 3, you can express 1 as such a combination with squares. So I can write down. Pardon me, Masha?
Where does it lie in A?
Just because it's this. But H alpha is in A, G alpha is in A, and their product is also in A. because A is a ring. So one is this combination. What was the combination? The sum of A alpha times H alpha squared. Okay? And now let's multiply. F is equal F times 1. So it's equal the sum of A alpha F times H alpha squared. And now this thing is in A, and that's a finite sum. Everything here is in A, so it lies in A.
We used compactness.
Yeah, we used that there was a finite cover, yeah, but it was an assumption. In our definition of algebraic varieties, no, so sorry. Here it's not absolute variety, but a fine variety. But okay, so you will prove in your home exercise that it's a quasi-compact, but it's somehow immediately seen from here.
В каком месте это понадобилось?
The finiteness.
Компактность, да?
Well, just for the finite, that this sum is finite. So this sum is finite.
Почему было бы плохо, если бы оно было бесконечно?
Then it doesn't make sense. There is no topology, so the infinite sums do not make sense. We can only use finite sums. Okay, so, well, I'm afraid I have to stop. I didn't prove yet somehow the most important thing, yeah, that it's an equivalence of categories, that morphisms between spectra are the same as morphisms between functions.
The spectrum is an affine algebraic variety.
Pardon me? Say it again?
Did you prove that the spectrum is an affine algebraic variety?
Yes, but the definition was, if you remember from the last time, the definition of a affine algebraic variety was that morphisms from any other algebraic variety to this one are the same as morphisms between global functions.
Yeah.
And we didn't prove this yet.
Yeah, that's what I'm talking about.
Yeah.
We didn't prove that the spectrum is an affine.
Right. So it's very short argument, but maybe I'll start with it next time. And I hope in your home assignment you don't need it, or you can use it for free. I will prove it next time at the beginning. Thank you.
Домашнее задание.
Вопрос? Да.
На каком языке их лучше писать?
Как угодно, абсолютно как угодно.
То есть можно и на русском, да?
Да, конечно.
Хорошо.